Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's unpack this. Today we're going deep into what scientists believe is the solar system's best chance for finding, extant life right now. We are talking about Enceladus, that tiny, icy, bright moon tucked into Saturn's vast family of satellites.
It's a remarkable world. For decades, it was just a statistical curiosity. But over the last 15 years or so, Enceladus has just fundamentally reshaped our understanding of where life can take hold.
Right.
It has moved from a cold, distant celestial body to a genuinely plausible candidate for hosting active life as we know it. And that is a monumental shift in astronomical perspective.
So our mission today is pretty straightforward. We want to give you a shortcut to being completely informed on this topic. Why is Enceladus, suddenly beating out Mars and even Jupiter's moon Europa in the race for astrobiological exploration?
That's the question.
We've pulled together the cutting-edge research focusing specifically on the powerful reanalysis of crucial data gathered by the venerated Cassini spacecraft.
And that reanalysis is the absolute key. The ability to sample the plumes, the material ejected directly from the moon's hidden interior, is an absolutely unprecedented opportunity in solar system exploration.
It's incredible.
And the reanalysis of that raw data has allowed us to overcome technical uncertainties and confidently confirm that Enceladus has all three pillars of habitability: liquid water, essential chemical building blocks, and a continuous energy source.
So we'll start right at the beginning. The initial breakthrough discovery that really put Enceladus on the map and set the stage for everything that followed. Before Cassini got there, Enceladus was primarily noted for being, highly reflective. It has some of the whitest, cleanest ice in the solar system. It was cold, small, and generally considered geologically dead.
Completely inert, yeah.
But when the Cassini spacecraft began its long, productive 10-year orbiting Saturn, operating from 2004 all the way through 2017, the script just flipped completely.
The pivotal moment came pretty early. In 2005, Cassini detected these massive, continuous geyser-like plumes.
And these weren't just, sporadic puffs of gas.
No, not at all. They were steady streams of water vapor, ice grains, and fine particulate matter erupting continuously from these long parallel fissures, what we affectionately call the tiger stripes, in the icy crust over the South Pole.
And the immediate, profound implication of that discovery, which is still what makes Enceladus so unique, is that the moon is actively delivering samples of its interior to space.
Exactly.
We didn't have to design some impossible mission to drill through kilometers of deep ice.
No, we could just fly right through the material it was ejecting for us.
Incredible.
Exactly. But this is where we encounter the initial challenge, one that the recent studies have worked so hard to overcome. It's the problem with proxies. When Cassini first detected these particles, much of the subsequent analysis was performed on samples collected far away, primarily from Saturn's E-ring.
Okay, so remind us about the E-ring and why relying on that material presented a challenge for determining habitability.
So the E-ring is the outermost, most diffuse ring in the Saturnian system, and it is almost entirely fed by the continuous stream of material coming off Enceladus. It's a vast, icy cloud.
Right.
The problem is that E-ring material is, scientifically speaking, not fresh. It has been floating in the harsh environment of space for potentially long periods.
And space is not kind to organic molecules.
It is not. Once that water vapor and ice material are exposed to the intense radiation within the Saturnian magnetosphere,
Just getting blasted by high-energy charged particles.
constantly, and the chemicals within can be significantly altered or even broken down. This process, it's called radiolysis, it can completely change the original chemical characteristics. It could give us misleading readings when we try to confirm the ingredients for life.
So early on, we were trying to read a message that had been partially garbled by cosmic rays. The scientists knew they had to find the freshest material possible.
That's right. But even those initial slightly compromised samples were revolutionary. The initial analysis revealed the presence of sodium salts. And that was the first massive, incontrovertible clue that this wasn't just a giant ice ball.
Why is sodium salt so important? It sounds mundane like table salt.
It's all about the context. For salts to be present, the plumes must be fed by an underground liquid water reservoir. And not just any reservoir, but one that is in active contact with the moon's rocky core.
Oh, okay.
Think about it. Water is the ultimate solvent. If water sits next to rock for geological timescales under high pressure, it will dissolve minerals. The salt content suggests the water is not just isolated in some ice pocket, but it's actually circulating through and reacting with the silicate rock at the bottom.
So that contact point water, rock, and sustained heat, that's the critical condition for geothermal activity, which is the engine for complex chemistry. It suggests a dynamic environment.
Precisely. It implies a warm, dynamic, high-pressure, water-rich environment where chemical gradients can form. This initial detection of salts was the foundational evidence, confirming the presence of a vast liquid brine interacting with silicate material, which is the absolute prerequisite for an environment conducive to chemosynthesis.
So the chemistry suggested a hidden ocean, and more importantly, a rocky bottom.
Right.
But the scientific process required physical confirmation of that ocean. The early data only suggested a localized sea near the South Pole where the plumes were.
Yeah.
How did the later physical observations prove the sheer scale of the water?
That leads us to the sheer physics of this world. The definitive confirmation that the ocean is global came from later, extremely precise observations of Enceladus's orbital mechanics, specifically its rotational dynamics, or what scientists call its libration.
I remember the term wobble being used, which makes it sound simple, but this was profoundly complicated orbital mechanics. What exactly were the Cassini instruments measuring to determine this?
They were tracking surface features on Enceladus craters, landmarks, that kind of thing, over the course of several years as it orbited Saturn. They were measuring the moon's slight predictable shifts in rotation relative to Saturn. If a body is entirely solid, if the ice shell is frozen rigidly onto the rocky core, it rotates as a single homogeneous unit. Its rotation would be extremely smooth.
Like a perfectly carved wooden sphere spinning on an axis.
Exactly. But if there is a massive global liquid layer between the core and the shell, the gravitational pull from Saturn affects the outer shell differently than the inner core. The shell ends up exhibiting a slightly larger, more pronounced oscillation or wobble than it would if it were solid.
And the aha moment was that the measured wobble was too large to be explained by a rigid body.
Far too large. The observation confirmed that the icy exterior shell is completely decoupled or detached from the rocky core below. The shell moves slightly independently, essentially floating on top of a massive liquid reservoir.
And that physical detachment is the ironclad proof that the ocean is global. It has to extend across the entire moon, sandwiched perfectly between the kilometers-thick icy shell above and the silicate core beneath. It's a world-spanning subsurface sea.
And just think about the implications of that. We have a moon where the average surface temperature is, minus 330 degrees Fahrenheit? Yet we know there is a body of liquid water, likely comparable in volume to Lake Superior on Earth, just existing beneath the ice.
Which immediately brings us to the next physical problem. How does that water stay liquid when it's so far from the sun?
And the answer is the internal powerhouse. Tidal flexing. It's the engine that runs this entire system.
Okay.
Tidal flexing is the process by which Saturn's enormous gravity generates internal heat. Enceladus follows a slightly elliptical, non-circular orbit around the planet. When the moon is closer to Saturn, the gravitational pull is stronger, and the moon is stretched or elongated. When it moves farther away, the gravitational pull weakens and it relaxes.
It's a perpetual cyclical deformation. We can think of it like continuously bending a piece of metal back and forth until it heats up at the stress point.
That's a really good analogy. That constant stretching and squeezing creates immense internal friction. This friction generates energy, which is dissipated as heat deep within the moon's interior, and it's specifically concentrated around the rocky core and the base of the ocean. This continuous heat production prevents the entire global ocean from freezing solid.
But if that heat were just generated uniformly across the body, it might not be enough to sustain the deep-sea conditions necessary for life, right? What's the specific connection between this tidal energy dissipation and the potential for life?
The connection is profound and geological. The tidal forces are strongest where the material is most resistant to deformation, and that's at the interface between the dense, rocky core and the liquid water.
So the heat is concentrated right where we need it, at the seafloor.
Exactly. So the expert insight here is that tidal flexing is providing the sustained energy required to drive rock-water chemical interactions. It's not just a thermostat keeping the water liquid, it's supplying the continuous geothermal power that facilitates complex chemical reactions at the seafloor.
Without tidal flexing, Enceladus would be inert.
Chemically, yes. With it, the physics and the chemistry are perfectly linked by Saturn's gravity to create a potential incubator for life.
And that dynamic heat source leads us right into the exciting chemical discoveries. But before we get to the chemicals, we have to talk about the toolkit itself. This brings us to the technical hurdle. How Cassini, traveling at phenomenal speeds, managed to grab these microscopic ice grains and decipher their molecular identities.
This is where we celebrate the ingenuity of the scientists and engineers. Cassini was equipped with a highly sophisticated suite of instruments designed specifically for this kind of reconnaissance, primarily the Cosmic Dust Analyzer, or CDA, and the Ion and Neutral Mass Spectrometer, or INMS.
Let's break down the process. Cassini was traveling at speeds sometimes exceeding, 17 kilometers per second, essentially trying to sample a puff of smoke.
And that velocity is critical to the measurement technique. The CDA was designed to analyze the solid particles, the ice grains. It didn't try to capture them. It relied on the high-velocity impact itself.
So describe the violence of the collection.
Imagine those solid plume ice grains hitting the detector surface at 10 miles per second.
Wow.
The collision is so energetic that it instantly vaporizes and ionizes the material. It breaks the solid ice grain into smaller electrically charged fragments. Once those fragments were inside the CDA, they were subjected to electric fields.
And that's the mass spectrometry part. How do the pieces tell you what they were originally made of?
Mass spectrometry works by measuring the mass-to-charge ratio. In this instrument, scientists use the precise timing of the flight path of those chemical fragments to determine their identity. Lighter fragments like hydrogen or helium accelerate faster through the electric field and arrive sooner at the detector. Heavier fragments like large organic molecules take longer.
So it's a reverse engineering process. You take the debris, measure how fast the pieces arrive, and then you can piece the jigsaw puzzle back together to figure out the molecular identity of the original ice grain that shattered.
And the INMS, on the other hand, focused on the gaseous components, the water vapor and other gases that hadn't condensed into ice. Between the two instruments, Cassini captured an incredible data set of both the gas and solid components being ejected.
Now let's bring in the centerpiece of the sources we analyzed. The recent powerful study led by Nozer Khawaja and his team at the Free University of Berlin. They didn't collect new data, they went back to the old Cassini archives. What did they find, and why did they succeed where previous analyses might have struggled?
They focused on a specific subset of data collected during a particularly fast, close flyby over Enceladus's south pole. This was a game changer because of two major technical advantages.
Advantage one.
Yeah.
The freshness of the sample, tackling that problem with proxies we talked about earlier.
Exactly. By flying extremely close and fast through the densest part of the plume, the team guaranteed they were analyzing material that had been ejected perhaps only moments before. This guaranteed the removal of virtually all possible radiation-induced interference. They eliminated the noise of space radiation, meaning the chemical readings are now far more representative of the pristine subsurface ocean chemistry.
We can trust the signal.
We can trust the signal.
So we can be much more confident that what they measured truly exists miles beneath the ice. What was the second technical advantage of that high-speed flyby?
The high velocity of the impact itself. Khawaja's team realized that the higher speed impact caused the solid plume material to fragment in a specific, energetic way. This fragmentation exposed and made detectable more types of molecules than had been visible in previous, slower flybys. It was like tuning the mass spectrometer's dial to a slightly different frequency, suddenly revealing molecules that had been previously masked or hidden beneath the noise floor.
That is the definition of a sophisticated deep dive, using superior analytical techniques on existing data to unlock profound new conclusions. They didn't need a new spacecraft. They needed a new algorithm and a deeper understanding of the instrument's physics.
And this reanalysis confirmed the presence of the crucial ingredients we need to discuss now, the building blocks of life.
With the chemical readings now certified as truly fresh from the source, we can move on to the actual inventory of life's ingredients. We are talking about the foundation of biology, the organics, the compounds necessary for Earth-like life.
The first box we look to check is the carbon connection. While our listeners know that organics are simply molecules containing carbon, what's exciting here is the complexity of the carbon compounds detected.
Carbon, of course, being that versatile element that can form long chains and rings, acting as the structural scaffolding for complex biology.
Right. And organics have been detected with high confidence in this reanalyzed plume material. And crucially, they weren't just simple hydrocarbons. The specific findings included molecules called amines.
Okay, let's focus on the significance of amines.
Amines are incredibly important because they contain nitrogen bonded to carbon, and they are crucial precursors to amino acids,
Amino acids.
which, of course, are the building blocks that link up to form proteins, which are the fundamental workhorses, the enzymes, the structural components of terrestrial life. Finding amines suggests that the underlying chemistry within the ocean is not random, but is actively engaging in the early steps of prebiotic synthesis.
So the ocean isn't just dissolving rock, it's building things. It's creating molecules that are already pointed toward the pathway of life.
Precisely. We are seeing molecules that represent the required chemistry to start assembling complex biological structures. This goes far beyond simply confirming water and heat.
Now, one of the most tantalizing bits of information from the reanalysis is the detection of much larger structures, what scientists refer to as macromolecules. This is where the story gets a little mysterious.
It truly is a mystery. Cassini's mass spectrometer, while revolutionary, had a functional mass limit. The data clearly showed fragmented pieces corresponding to very large molecules, much larger than the simple amines or the fragments of water ice. The mass spectrometer could tell they were large, complex, and carbon-based, possibly with nitrogen and oxygen embedded.
But the violent nature of the high-speed impact meant that the original structure of these macromolecules was lost in the fragmentation. We know something big is there, but we can't read the structural blueprint.
It's highly suggestive. These could be complex, polymerized organic compounds, or potentially even large biological remnants if life exists. The fact that the detection is consistent across multiple flybys reinforces the idea that the ocean is rich in large, complex organic matter, even if we can't yet identify their specific structure. This limitation is why the next generation of instruments is so vital. They must be designed to handle and characterize these larger molecules.
Even without fully characterizing the macromolecules, we can complete the habitability checklist based on the core elements required for life on Earth, what we call the CHNOPS elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur.
And the scorecard is impressive. Carbon, hydrogen, nitrogen, oxygen, and phosphorus have all been detected with confidence in the plume material.
5 out of 6.
5 out of the 6 essential elements are present in a vast liquid water environment that is actively interacting with rock and heat. That's an overwhelming positive signal.
Wait, let's pause on the missing piece. Sulfur. If we are aiming for comprehensive habitability, why is sulfur the one element not yet confirmed with confidence? What are the implications of that?
It's a fascinating puzzle. Sulfur is essential for life. It forms part of certain amino acids like cysteine and methionine and is crucial for many enzymatic processes. On Earth, we find sulfur compounds everywhere, often originating from hydrothermal processes, volcanism, or dissolved minerals like sulfates.
So if the ocean is interacting with the rocky core, wouldn't we expect to find some sulfur compounds dissolved in the water?
Logically, yes. The rock core itself is likely rich in iron sulfides. One theory is that the particular fragmentation process of Cassini's mass spectrometer may not have been optimal for detecting sulfur-bearing ions, or perhaps the sulfur compounds are in a phase that is less likely to be ejected through the plumes, maybe remaining locked in minerals on the ocean floor.
So the absence of detection isn't necessarily proof of absence, but rather an indicator of a technical limitation or a nuance in the deep-sea geochemistry.
Exactly. Given that the other 5 elements are present and the conditions are right for rock-water interaction, scientists generally assume that sulfur is likely present in some form. Even if the current data hasn't given us the definitive confirmation needed for the checklist, the discovery of phosphorus earlier in 2023, confirmed through similar reanalysis techniques, really sealed the deal on the elemental requirements.
So if you were building a biological system from scratch, you have almost all the necessary scaffolding, raw materials, and mineral nutrients present in the subsurface ocean. But as we know, raw materials alone don't power life. You need a continuous source of energy to drive the chemical reactions and sustain metabolism.
And that takes us to the most compelling piece of evidence provided by the Cassini data confirming the fuel source: the contrast between chemosynthesis and the unlikely scenario of photosynthesis.
Well, the sun is clearly out of the running here. The ocean is buried under kilometers of dense ice. We are talking about absolute darkness.
Highly unlikely for photosynthesis, yes. So we have to turn to the alternative energy pathway, which revolutionized biology on Earth when it was discovered back in the 1970s: chemosynthesis.
The idea that life doesn't need sunlight. It can metabolize chemical compounds and minerals.
Precisely. On Earth, this happens most famously around deep ocean hydrothermal vents. These are fissures where scalding hot water, enriched with minerals like iron, methane, and hydrogen sulfide, emerges from the crust. Microbes perform chemical reactions using these compounds for energy, forming the basis of a self-sustaining ecosystem completely divorced from the sun. If life exists on Enceladus, this is almost certainly its power source.
And what specific, definitive chemical evidence did Cassini provide that supports the existence of these chemosynthetic vents on Enceladus' seafloor?
The mass spectrometry results pointed directly to the necessary ingredients. We detected carbon dioxide, methane, and most critically, abundant molecular hydrogen, text Hu22.
Hydrogen is common everywhere in space. How can we be sure that the quantity detected implies active hydrothermal vents and isn't just background chemistry?
That's the critical question. And the amount of hydrogen detected in the plume material is staggering. It is so voluminous that it requires a present-day, active, high-volume source within Enceladus's ocean to explain it. Hydrogen is chemically reactive. It doesn't just linger in such high quantities over geological timescales, it would react with other compounds.
So the immense quantity proves it is being actively generated right now.
It is the smoking gun of ongoing geological activity. And the specific mechanism that generates this level of hydrogen when water interacts with a rocky core under high pressure and temperature is a process called serpentinization.
Tell us about serpentinization.
Serpentinization is a common geological process on Earth. It happens when water circulates down through the porous, rocky crust and reacts with iron-rich silicate minerals, particularly olivine, at temperatures well above 300 degrees Celsius. This reaction converts the mineral into serpentine, hence the name, and crucially releases massive amounts of molecular hydrogen and methane.
So if serpentinization is occurring in Enceladus's core, that means the moon is essentially creating the ideal chemical fuel for life.
It confirms not just water, not just chemicals, but an active, ongoing energy-generating engine. One that mirrors the exact process that powers the most robust ecosystems on the deepest parts of Earth's ocean floor. It means the conditions are not just possible for life, but are being maintained in the present day.
And the Quadra reanalysis strengthened this conclusion, correct?
Absolutely. By analyzing the freshest plume material, the team confirmed known substances and also included new, complex organic substances that further hint at this specific hydrothermal origin. For instance, the detection of certain complex nitrogen and oxygen-bearing compounds is consistent with what you'd expect from high-temperature water rock synthesis.
So the overall conclusion is powerful. We have the solvent, water, the structural materials, organic CHNOPS, and the power source, chemosynthesis driven by active serpentinization. We've minimized the uncertainty previously caused by radiation, and we know the energy gradient needed for chemosynthetic life is constantly being supplied.
Enceladus is not a historical curiosity. It is a chemically active world right now, demonstrating a dynamism that few people would have predicted a couple of decades ago.
With the scientific case for habitability now complete and virtually ironclad, the final, most important question remains. How do we actually look for life itself? The next chapter is all about designing the future mission to find a definitive answer.
We must first summarize the significance of Cassini's final, reanalyzed dataset. The targeted analysis of freshly ejected plume material removed the major problem of radiative alteration. This confirms that the detected molecules, from complex amines to the overwhelming hydrogen concentrations, truly originate from within Enceladus's global active ocean. This makes the search for life much more focused.
It provides the mission planners with immense confidence. We know exactly what environment we're dealing with. What are the space agencies planning now?
The European Space Agency, ESA, is heavily invested in mission planning, currently centered around a concept known as the Enceladus Explorer. The mission is planned to launch sometime in the 2040s, which, for interplanetary travel, is essentially tomorrow.
What are the specific technological advancements needed for this future mission, compared to the limitations Cassini faced, like that macromolecule mystery?
The new mission will perform multiple, highly precise flybys of the plumes and potentially even achieve orbit. The crucial part is the massive upgrade in instrumentation. These new spacecraft will carry an entirely new generation of mass spectrometers and chemical analysis tools.
Tools designed specifically to address the structural uncertainty of those large carbon-based molecules.
Exactly. They need to provide higher mass resolution and be capable of separating and identifying extremely complex, large molecules without destroying the structural information upon impact. The new instruments will be specifically calibrated to look for definitive biological signatures within the plume material itself.
Things like long-chain lipids, chirality.
Chirality, the handedness of molecules or molecular patterns that are statistically unlikely to be formed by purely geological processes.
Right. That level of sensitivity required for this search is truly astounding. It speaks to the hope scientists have that the evidence isn't hiding miles beneath the surface. It's right there in space, waiting. I was particularly struck by the research from Fabian Klenner and his colleagues from the University of Washington regarding minimum detection limits.
Their work provided immense encouragement for this type of sampling mission. They demonstrated, through laboratory simulations of the impact process, that the detection capabilities of these advanced mass spectrometers are now so refined that even the material contained within a single bacterial cell traveling inside an ice grain ejected from the plume could potentially yield a detectable biological signature.
That is immense, because it means we don't need a thriving, dense population of microbes to find evidence. A single lucky microbe ejected from the deep sea into space could be enough.
If life resides around those hot, mineral-rich hydrothermal systems at Enceladus's depths, the journey it takes up the fissures, through the high-pressure environment, through the ice, and out into space, is long and arduous, and likely destructive. But even if only a minuscule fraction of biological material survives that transit, the evidence may be floating in space, waiting for us to find it with the right tools in the 2040s.
The confidence derived from Cassini's data is what fuels this next generation of exploration. The moon is doing the drilling for us. We've covered a remarkable distance in this deep dive into Enceladus. Let's just synthesize the key components for you. We started with the physical conformation of the global ocean, proved by the rotational wobble, and kept liquid by the sustained energy of tidal heating driven by Saturn.
We then detailed the critical technical advantage of the recent research, the use of fresh plume sampling data, which successfully removed the problem of space radiation interference, allowing us to trust the chemical readings implicitly.
This allowed us to confirm the presence of key organics, like amines, crucial precursors to proteins, and almost the entire set of CHNOPS elements necessary for life, alongside the tantalizing mystery of complex macromolecules.
And most critically, the data pinpointed the active energy source. Massive, ongoing levels of hydrogen in the plume, which demands continuous chemical activity, most likely from hydrothermal vents driven by the serpentinization process on the rocky seafloor.
This provides a comprehensive, unified understanding of why Enceladus has surpassed every other icy world as the most compelling current target in the search for extant life. The ingredients are there, the energy is flowing, and the moon is actively sharing its secrets with us.
The case for habitability is solid, but we must leave you with a final provocative thought, one that acknowledges the immense difficulty of the search ahead.
We established that even a single cell could theoretically be detectable if it's ejected into space. But consider the journey we've outlined, the long and arduous transit through kilometers of superheated, high-pressure liquid, possibly passing through thermal extremes, then freezing and embedding inside an ice grain, and finally being blasted into the harsh vacuum and charged radiation environment of space.
That process is a trauma. If life does reside in Enceladus's hot deep-sea systems, how might that intense journey have degraded, evolved, or fundamentally altered its chemical signature by the time it reaches the detector in the 2040s? Will the fragile biosignatures remain intact enough for our instruments to recognize them as unambiguous evidence of life? And what are the ultimate implications if, despite this phenomenal scientific preparation, we don't find evidence on the first highly sophisticated attempt? Does that imply the ocean is sterile? Or does it simply mean the universe has found a way to obscure the smallest signal just slightly better than our detection systems can perceive? That is the scale of the challenge that awaits the next generation of deep space explorers.